So I'm going to talk about an example for Kirchhoff's first and second law. So we have a circuit here, and we are asked to find the current through R1, R2, and R3. So let's start off. Let's say that the current coming out here is I1, which is equivalent to the current here, which is also I1. However, here there is a junction, so the current diverges. So let's call this I2, and let's call this I3. And you may be wondering, why it has to be in this direction. Why can't be this direction? Or some other combination of I1 and I2 and I3. Yes, this will only affect the sign of the equation. You might, in the end, get a negative current. But the magnitude is the magnitude of the current. The negative means that it should have been positive all along. So what I mean by it should have been positive or should have been negative all along, it means that, for example, if we say that I2 is going in this direction and I1 is going this direction, that means this is I3, but we find that I2 is negative, it means that this is right. I2 was supposed to go up in that direction. That's what it meant. So we could find to solve these equations, we need to find simultaneous equations, and we could get all of these simultaneous equations from Kirchhoff's first and second law. So from the first law, we can say that I1 equals to I2 plus I3. That's the first one. And from the second law, let's take a look at a loop. Let's look at this loop right here. We could get that, let's say that this is a positive potential change. This is negative, this is positive, and I'm going in this direction. So this is a potential increase. Great. So I'm moving along this way. Resistors cause potential decreases. So here there's going to be a potential drop. Here, because I'm going from the positive end of the battery to the negative end, this is also going to be a drop. And if I go here, keep going, I go up to the I2 direction, go here, it's going to be a potential drop again. And I get back here. So what I will get is that epsilon 1 minus I1 R1 minus epsilon 2 minus, notice that the current changes here. The current changes in this direction. So we're going to get I minus I2 R2. Notice that it's along the direction of the current flow. And that will equal to 0. And let's get a third equation in. And our third equation, we could use this loop. And let me get some stuff out of the way. Okay, this is I2. All right, so this will be a little tricky. So if we look at this loop right here. Okay, so the current I3 will go from here to here. This is negative, this is positive, so this is a potential increase. Okay, so far so good. There's a potential increase as well. There's a potential decrease. There's a drop here. However, if I go down here in this direction, it should be I2, but I set I2 in the upward direction, but right now I'm going down. So that means it's negative. So that means there is a potential drop, which is negative. So what we have here right now is epsilon 3 minus I3 R3. But resistors give potential drops, so it should be minus I2 R2. However, the direction we're going, I2 is negative. So this should be a positive sign because we're going in the opposite direction. Our current is going in the opposite direction. So I2 should be negative. So they should be positive. And now we have three equations, and if we know what epsilon 1, epsilon 2, and epsilon 3 is, and we know the magnitudes of the resistors, we could get three simultaneous equations. We could get these three simultaneous equations, and you could chuck them in a calculator and define the values. But this is how we find the equations for a circuit. And usually, if there is a fourth unknown, for example, if there's a fourth unknown in this circuit, we could always look at this one. We could look at the bigger loop. And that will be all.